Alright, this video talks about section 2.2, some specifics dealing with Hamilton circuits, or as they are also known, Hamiltonian cycles. Alright, so in terms of what we're going to look at, first thing is there are three main theorems in your textbook in this section, as he very uncreatively calls them theorem 1, 2, and 3. So the first theorem is due to Dirac. I'm sure I'm mispronouncing that, but what it says is suppose you have some graph, you've n vertices, so you have at least 3 vertices here. You're going to have a Hamilton circuit if the degree of each vertex is at least half the value of n. So this is literally looking at something like, let us give ourselves a little bit more space here so I can put in a little hint of an example. So here, what this literally is telling you, let's color code this for ourselves. So here's what this means. So you're looking at the degree of each vertex has to be greater than or equal to the total number of vertices in the graph divided by 2, and this is for all vertices. Okay. Now, if we actually look at a teeny tiny baby example, suppose you have a graph G. So G has, I don't know, let's be super lazy. G has 4 vertices. Now, what would that mean that you're looking for if you wanted to apply this theorem? This would mean that for each or for all, so for all vertices in your graph, you would need the degree of each of those guys needs to be greater than or equal to 2. Okay? And if you have that, then you should be able to find one of these Hamilton circuits, or as they're also known, Hamiltonian cycles. Okay? So that's the first theorem. Second theorem is by Chvátal, and this one here says, all right, well, what happens if you have a graph? It's a connected graph with n vertices, and this one here actually gives you what the vertex set is. So we just labeled the vertices vertex 1, 2, 3, etc., all the way down to n, whatever n actually is. Now here's what this one is talking about. It actually gives you an inequality in terms of your vertices. So in terms of how you label these vertices, you're labeling vertex 1 through vertex n, where the vertices with the smallest degrees are going to be listed first. So if vertex 1 has degree 2, vertex 2 has to have degree 2 or bigger. So if vertex 2 has degree 3, then all the other vertices have to have degree 3 or bigger. So it literally orders them by their degree. Okay? So whatever they were originally labeled, you relabel them like this. So that's what that part's telling you. Now here's the condition in order to get your Hamilton circuit. In this case, it says, so if you look at the first half of these vertices, you either have to have those vertices to have their degree greater than k, or the symmetric vertex needs to be less than n minus k. Okay, so let's see what that would look like, and I'm going to do a really baby example. So this one here, suppose again we have 4 vertices. So a little baby example. Suppose we have a graph, and this guy has 4 vertices. In terms of how to use this theorem, when you write out your vertex set, so this would be V1, V2, V3, V4. Notice the ordering here tells you that the degree of vertex 1 is the smallest. Maybe they actually all have the same degree, that's totally fine, but the order of the degree, in other words, it's going to be listed in increasing order. Okay, so that's one thing it says. Now, the actual condition down here tells you that if you look at k, so for all k that's less than or equal to n over 2, so in our particular case, what would those k's be? This is talking about k equals 1 or k equals 2. You have to have one of 2 conditions. Okay, so when k equals 1, what are you going to have? You're going to be looking at the degree of vertex 1 has to be bigger than 1, or you look at the reciprocal vertex, so this would be the degree of vertex, and n minus k would be 4 minus 1 or 3. And that has to be bigger than, well, 4 minus 1, which would be 3. Okay. Now, if we looked at k equals 2, well, this one doesn't help us too much because if you actually 2k equals 2, well, So this would be degree of vertex 2 needs to be bigger than 2, or, and this is why I went degree of vertex 2 has to be larger than, well, do the same subtraction here, you're still going to get 2. Okay. If you have more vertices involved, you'll actually get where you're looking at in this list of vertices that you have, you'll walk it from the two ends and pull it, you're looking in here. And that either or is where these inequalities are going to actually fall. Okay, so that's this one. In terms of our class, I'm really not going to ask you to use this theorem unless you decide that you really want to use it. Okay. So that's the first two theorems. The first two theorems, relatively straightforward. The third theorem, however, feels a little bit snarly. So this theorem attributed to Grinberg talks about a planar graph. So in a planar graph G, it's going to have one of these Hamilton circuits or Hamiltonian cycles. We're going to call this circuit H. And so we're going to let R, I'd probably write this with F because here is going to be the number of faces inside of your Hamilton circuit that are bounded by I edges, and Ri prime is going to be the number of faces outside of H bounded by that same number of edges. So remember, bounded by blank edges is the same as looking at the degree of your face. So this here, Ri, is the number of faces with degree I, except not really, because notice there's this distinction between where those faces are inside the Hamilton circuit and outside the Hamilton circuit. And if you actually count up all the faces with degree I, that doesn't actually mean there's nothing on there that requires you to be inside or outside of a circuit. So if you actually want the total number of faces of degree I in your graph, that would be where you add up these two guys. Okay, so that's sum. Now, then Grinberg tells us that we actually have a formula, and this is the key thing in this particular theorem, right here, that if you take I minus 2 multiplied by the difference of the number of faces with degree I that are inside the circuit versus outside the circuit, you do that then for each I, so I being the different number of edges that would bound your face, when you sum it all up, it'll equal 0. Now, please note, it's only going to equal 0 here if you actually have that Hamilton circuit. So how is this guy useful? If you actually have the Hamilton circuit, you can pull out this formula and you can actually solve for the number of faces. But on the flip side, if you can actually figure out what this formula is, if you can determine that it would never equal 0 no matter what you do, that's a way of showing that your Hamilton circuit actually doesn't exist. Without just grubbing through the graph and being like, oh no, what's going on? I can't find one. I think I've exhausted all the possibilities. So instead of trying to actually brute force it, this would be a way with a formula to show that you wouldn't have a Hamilton circuit. So let us look at an example, and this is totally the exact same example that is in your book right next to Theorem 3, but I wanted to do it again, not because it wasn't a good example, but because the way that your book describes it is just, it feels like he's missing key steps when he talks about it, okay? So if we look at this example right here, it's going to be an application of this Theorem 3, so we're going to apply this here of dealing with, does the Hamilton circuit exist? We're going to look at your faces that are bounded by a certain number of edges or that have degree I, and then we're going to look at that formula. So I'm going to scroll up because you can't actually see the graph. So if we scroll up to this graph looks like this, okay? So it kind of looks like a honeycomb. You've got these 3 edges right here that look like little hexagonal shapes. You've got faces. You've got these 3 faces right here that look like little parallelograms, and then you've got these ones where I had to curve the lines, okay? Now, we could totally go in and actually let me do that. Totally go in and mark each of these faces, but because we want to focus on faces that are bounded by a certain number of edges, instead of labeling the faces like we have in the past with an F and then a subscript, I'm going to go in and just label them based off the number of edges that are bounding the face. So on the bounded faces, we'll do that, and then we'll do the same thing on the unbounded face last. So up here at the top, and I'll start off with all these guys with straight edges first. Up here at the top, you've got this parallelogram shape. So this is a face that has 4 edges bounding it. So it's degree 4. We've got these 3 hexagonal shaped guys, so make sure they really are hexagons. Yep, you've got 6 edges bounding each of these hexagonal shaped faces. So those are faces with degree 6. And you've got these 2 other guys that look like parallelograms. So these are 2 more faces of degree 4, or 4 edges creating those bounded faces. Then we've got the 2 weird shaped faces, this guy and this guy with the curved lines. So let's see what their degrees are. So we've got, starting at Q here, I'm just going to go around clockwise. So 1, 2, 3, 4, 5, and then curved line is 6. So there's a face with 6 edges comprising of it. And it looks like this other one's going to be the same thing, but let's confirm. So starting here at Q, doing the same thing. So 1 edge, 2 edge, 3 edge, 4 edge, 5 edge, and then the curved edge, so that makes 6. So then we have right there 6 for our degree of that face. Now, lastly, the unbounded face. So out here, our unbounded face. First time I actually did the proper name. And if we look at the number of edges comprising that unbounded face, or the degree of that face, let's walk around starting at Q like we did before, just to be consistent. So I'll go around and do counterclockwise here. So we've got 1 curved line, 2, 3, 4, 5, and 6. And we get back to where we started. So the unbounded face is comprised of 6 edges, those edges that create the, if you will, large perimeter around your graph. Okay. Now, notice what that means in terms of what we're dealing with our formula. What we just found was that, and I'm going to make like a little bullet point of the stuff we find here. All of our faces, so all faces, are comprised of either 4 or 6 edges. Okay. If we look specifically at, so I'll maybe make a little arrow so it doesn't look like a minus sign. If we look specifically at our 4 edge guys, if we actually, since we don't know where the Hamilton circuit is, I'm going to go ahead and add up the total number of faces that have degree 4. So this would be all of the degree 4 faces that are inside of whatever Hamilton circuit may exist, and then all the ones that are outside whatever Hamilton circuit exists. And since we don't know where that Hamilton circuit is, we don't actually know what R4 and R4 prime equal, but we know the sum is all of those degree 4 faces, and if you add them up, it looks like there's 3 of them. 1, 2, 3. Yep, that looks like all of them. Now we can, and this here is just to make sure we're all on the same page. This here, I equals 4. Okay. And if we look at the degree 6, or the 6 edge guys, we can do the same thing. So here, I'll go ahead and add up the faces that have degree 6, both inside and outside of any potential Hamilton cycle or Hamilton circuit here. And we got how many? The unbounded face, so 1, 2, 3, 4, 5, and 6. And if we want to do this in terms of i's, this would be I equals 6. Okay. So if we then applied our formula, so this is the formula from theorem 3, as I abbreviate theorem there. This says you have the sum of, add up over I, of I minus 2 times Ri minus Ri prime. And we want this thing to equal 0, or it's supposed to equal 0 if the Hamilton circuit exists. Okay. Now, in this case, the only i's we have are actually I equals 4 and I equals 6, which is why I went ahead and put them over here. So they're the only ones we're actually going to add up over. So if we put this together, what are we going to have? Well, if we look at I equals 4, so I equals 4, I equals 4 minus 2, well, that's going to be 2. And then we'll have R4 minus R4 prime. If we then look at what happens when we have I equals 6, and this whole thing's supposed to equal 0, we'll have R6 minus R6 prime. And the coefficient out front is going to be I minus 2, so 6 minus 2, so that'll be 4. Okay, so this right here is the formula that has to be true if we've got the Hamilton circuit existing in this particular graph. Okay, now here's the claim. So we're now below the graph. Claim. I am going to claim the following. I'm going to claim that this difference on the R6s, so the faces of degree 6, the faces with 6 edges, I'm going to claim that that guy can't equal 0. Okay, so that's the claim. Now, why is that true? Well, let's check it out. If we actually had that difference equaling 0, what would happen? Well, it would mean a couple of things. The first thing that it would tell us is it would tell us that the number of faces with 6 edges inside versus outside our Hamilton circuit has to be exactly the same. Now, what do we know? Total number of faces with 6 edges, when you added it together, was going to be 6. So if the sum is 6 and these two guys are the same, well, they both have to equal a grand total of 3. Okay, so this first equals was from the difference formula right here, and that second equals was from where we literally just counted up the total number of faces with 6 edges. Okay, so that's the first thing that would happen. Now, if we then look back to our formula, if this second term equals 0, and how would we know the second term equals 0? Well, if the difference of the R6s equals 0, that means this whole thing would obviously 0 out. So cross this off, it's gone. Then what would happen if 2 times the difference of the R4s equals 0? Well, that means this difference of R4s would have to be 0. So let me label where we're coming from. So this one, first one, came from R6 minus R6 prime equals 0. And this one came from the fact that the sum had to equal 6. And let's star this formula that we were talking about. So star. So from that formula that was the star, we would get that R4 minus R4 prime has to be 0 once we plugged in all the other bits. Well, if that's true, the same thing happens that we just did up here. This would imply that you have to have the number of degree 4 faces that's inside your supposed Hamilton circuit and outside your supposed Hamilton circuit has to be the same. Well, what do we know? We know that the sum of those two together was supposed to equal 3. So if these two are exactly the same, this would tell us that not only are they equal to each other, they would actually be 3 over 2. Now, remember what these things are counting. This is the number of faces of degree 4 inside your Hamilton circuit and outside your Hamilton circuit. Well, it's counting how many of them there are. You're not allowed to have half of a thing. So this is something that can't exist. And this little symbol here that I kind of butchered in the symbol is supposed to look like 2 arrows touching each other at the arrow point. So it's supposed to be like there's an arrow and there's a second arrow. And that's a symbol for contradiction. That's a symbol in math to indicate that, nope, this can't happen. Well, since this can't happen, you go back to your assumption. And our assumption over here was, at the beginning, if the difference was 0, then all this other stuff happened. There was no issue here. There was no issue here. The issue came into the fact that we got a fractional number. Now, what does that mean? That means this initial assumption right here is wrong. And that's why we actually get that this difference can't equal 0. Now, moving on to the information when the difference can't equal 0. In other words, there's not the same number of faces with 6 edges both inside and outside your Hamilton circuit. Let us look to see what that means. So since we know that the sum, or the total number of degree 6 faces in our graph was 6, well, we can actually figure out what the cases are. Okay? So I'm going to specifically look at our non-negative integers. Why? Because R6 and R6 prime are dealing with who? You're literally counting up how many faces are inside or outside of your circuit. And just to make sure we're all on the same page, if you have a graph and say this is the Hamilton circuit, your faces so if that's the Hamilton circuit, I'll make it dark. I probably should have made it a different color. These would be the faces that are inside the Hamilton circuit, all those guys. So I'll put little dots. Doop, 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 doop. And then whatever faces are out here, these guys would be the ones that are outside the Hamilton circuit. Okay? And the Hamilton circuit can't cut through a face because it follows edges. Okay? That's why you can't have this 3/2. Now, if you look at your pairs of non-negative integers that are going to sum to 6, so possibilities for solutions for R6 and R6 prime, what can you have? Well, you could have 0 plus 6, so either all the faces could be inside the circuit or all the faces could be outside the circuit. You also have 1 and 5, so exactly one of the faces is inside the circuit or one of the faces outside the circuit. You could have 2 and 4. Notice I'm just doing pairs of integers that sum to 6 that are, well, we included 0, but so non-negative. And then you could have 3 plus 3. Now, what do we know? We already showed that if we actually had 3 plus 3, crazy and stupid things happen, so that's not really an option. Okay, so I'll cross it off. Now, what are we going to do on the second side? This is going to be our difference. So in our actual formula that we care about, we want to know what is R6 minus R6 prime, and instead of doing all the possibilities of which one of these is R6 versus R6 prime, because there's actually 6 cases, I'm just going to go ahead and do the absolute value. Okay, so we'll just subtract. So if you subtract 0 and 6, absolute value of that difference would be 6. If you subtract 1 and 5, the absolute value would be 4 of that difference. If you subtract 2 and 4, that would be 2 for the absolute value. And I say absolute value because what happens if you subtract them in the opposite order, you get the same number but negative, so absolute value just says just subtract the smaller one from the bigger one. Okay. Now, what does this tell you? This tells you the following. This says that if you look at the absolute value of the difference of the number of faces that are either inside or outside of your Hamilton circuit, it's going to be 2, 4, or 6. Or if you want to be lazy, you can say, hey, it's going to be 2 or bigger. But you could legitimately say it's only those 3 numbers too. Now I'm going to check to see what would happen if you look at 4 times the difference. Well, 4 times the difference of R6 and R6 prime is going to be what? Well, you multiply 4 by each of these guys. So this would be 8 or 16 or 24. Or to be lazy again, to do one inequality, it's going to be 8 or bigger. Now, why would I have picked on the 4 here? This is totally jumping back to our formula from the Theorem 3. So we're looking at this term. So what we just found is this term right here has to actually equal 8 or bigger. Specifically, it's only got 3 possibilities, 8 or 16 or 24. So next we're going to do some analysis right here, figure out what that one is. Okay, so I'll write down what I just talked out. So if 4 times R6 minus R6 prime is greater than 8, in order for us to have our formula work, so 2 times the difference of R4 minus R4 prime plus 4 times the difference of the 2 R6s equals 0. What do we need? We need this other term, the 2 times R4 minus R4 prime, to match up, right? Because these 2 terms add together to be 0. So if this one's 8, that one has to be negative 8. But if we do it in terms of differences, that means this guy has to be greater than or equal to 8 in terms of the differences. So the absolute values here are just cutting off who's negative and who's positive. Okay, so this one here was going to be 8, 16, or 24, and technically, if you don't worry about the absolute values, you'd have the 3 other possibilities, negative 8, negative 16, and negative 24. And this one has to be those same 6 possibilities, the positive and negative versions, but flip the sign. Okay, so let's check to see if that actually happens. Do we actually get, to make it easier, in absolute value, do we actually get that this term is 8, 16, or 24? Okay, so if we look now at the faces with 4 edges. So here's the stuff we know about these guys. We know that in our graph, the total number of faces with 4 edges, there's 3 of them. Okay? And so if we do that same little chart that we did with the faces with 6 edges, we'll look at the pairs that will actually add up to 3. And we're only going to look at the non-negative integers that add up to 3 integers because these numbers represent how many faces do a certain criteria. So you can't have negative and you need integers because it's counting up. Okay? So you could have 0 and 3 add up to 3. You could have 1 and 2 add up to 3. And honestly, those are the only options if you don't worry about which of these pairs match to either the R4 or the R4 prime. Okay? So those are the only pairs of numbers, that non-negative integers that add up to 3. Now if we then look at the difference, so that would be the R4 minus R4 prime, what happens? Well, if we take the absolute value of the difference, we're just going to subtract these numbers. Well, if we subtract 0 and 3 and take the absolute value, we'll get 3. If we subtract 1 and 2 and take the absolute value, we'll get 1. Okay? Now, what does that tell us? That tells us here that this difference, so R4 minus R4 prime, is what? It's either going to be positive 1 or 3. Okay? So if we're lazy, we can do an inequality like we did before and say it's smaller than 3. Now, of course, it's way more specific. It's either going to be 3 or 1. Now, if we then multiply this by 2, and specifically why are we doing that? We're trying to look for this term right here. So we'll multiply 2 by what we just got, and notice what happens when we multiply 2 by what we just got on the line above. We'll get a 6 on the other side of the inequality. Now notice what you actually get. You'll actually get that this expression in terms of absolute values is either going to be 6 or 2. Now notice what it had to be. It had to be from the previous work, the same thing as the values we got up here. So this guy was positive or negative 8, positive or negative 16, and positive or negative 24. What we just found with this term is it's going to be, well, when you multiply these guys by 2, we'll get 2 and 6. It's positive or negative 2 and positive or negative 6. Do any of these guys match up? Like, because if even one of them matches up, so like if one of these numbers match up with one of these numbers to equal 0, that would be how we would solve for the R4, R4 prime, R6, R6 prime. But as I'm sure you guys have already noticed, none of these numbers match up at all. So what is our conclusion? Because we needed 2 times the absolute value of the differences of the R4s to be bigger than 8, and in fact it's less than 6, those guys are incompatible, which means here's our conclusion. It doesn't matter what we do. This formula of 2 times the difference of the R4s plus 4 times the difference of the R6s, there is no way that we can ever get that thing to equal 0. Doesn't matter what we've tried to figure with the algebra, it will never equal 0. So what this means is that by our theorem 3, which I abbreviated right there, no Hamilton circuit exists for this graph. Please note, all of this work was for that original funky looking graph that kind of looked like a honeycomb. This is a procedure you can apply to any graph, but the work we did here was very specific to our original sort of honeycomb looking graph. And that's how to apply Theorem 3.